Alright, geometry for October 19th through 23rd. Please make sure that you have lesson 12 in your site so you can follow through with this. Alright, so we're going to take a new turn, and we are going to go away from proofs for just a little bit. And we are going to start talking about transformations. Alright? You have talked about transformations before. One, because I know I taught them to you in 8th grade. We spent quite a bit of time with transformations. Reflections, rotations, transformation or translations, that kind of thing. So really quickly, our opening exercise is kind of a quiz over certain things that we've been talking about. So I want you to pause the video, and I want you to answer these questions. Alright? Find the measure of each letter and angle in the figure below. So you can do this a couple of different ways. You can just go through. So I want to know about A. Looking at A, I know that I have two parallel lines. Here's my transversal. So A is, I'm going to use 65. So I know that this angle is 65 degrees. So what do I know about these two angles? They are a linear pair. So 180 minus 65 is 115 degrees. All right? Let's look at B. You've got to find angle B here. Angle B is right here. Once again, I can look at this as a linear pair, 115 degrees. All right, let's move to angle C, which is right here. This one's a little different. It does not talk about parallel lines here anywhere. So how might I go about figuring out what the measure of angle C is? Well, I know this is 88. What else might I be able to use? Any thoughts? I don't have any, I don't have a triangle here. Like I said, I don't have parallel lines. But what if I drew a parallel line here? What if I extended my parallel line here? All right, maybe that would help, possibly. You should have figured out that angle C was 67 degrees. All right? We'll come back here in just a few minutes to talk about that. Let's look at D. Well, if I know this is 88 and this is, maybe we can skip D and go to E, because that might help us. But if you figured out D is 23, if we have time, guys, we'll come back to these. E was 115. F was 124. G was 101. H was 79. I was 79. And J is 101. All right? All right, let's go to the next part. And guys, just because I want to actually get into part of the lesson, we're going to run through these quickly. We're given that the measure of angle CDE, so this angle right here, is equal to the measure BAC. So it's equal to that measure. And it wants us to prove that angle DEC, this angle, is equal to ABC, is equal to this angle. Alright, so we're going to start off with our given, the measure of angle CDE. is equal to the measure of angle BAC that is given. Alright. Now what do I know about the measure of the angles of a triangle? We proved in the last lesson that they were 180 degrees. So I can say the measure of angle CDE I'm going to look at this little triangle here, plus the measure of angle DEC, or DCE, plus the measure of angle, so I've got CDE and DCE, so let's do DEC is equal to 180, alright? The sum of the angle measures equal 180. Okay? So I know that all of these equal 180. Alright? So now let's look at the big triangle. Because what we're going to see is we're going to kind of compare both triangles here. So the measure of angle BAC plus the measure of angle DCE, because notice they share that angle, plus the measure of angle ABC equals 180. Once again, sum of angles in a triangle equal 180. So I've now proven, I know that my small triangle equals 180. I know my big triangle equals 180. Alright, so now let's think about this. I can do substitution property. They both equal 180. So I can say that the measure of angle CDE plus the measure of angle DCE plus the measure of angle DEC is equal to the measure of angle BAC plus the measure of angle DCE plus the measure of angle ABC. Alright? So now think about this. I want to prove that DEC is equal to A. So I want to prove that this is equal to this. So that means I need to figure out how to get rid of some of this. Alright? So I need to figure out how to get rid of some of this. So I can do some subtraction here. And if I do subtraction property, then I can prove that my angles are equal. Okay? And prove my angles are equal. Alright. So now, this is the part of the lesson that I wanted to get to. So it talks about partnering. Obviously we can't do that. We can't even do that in the classroom. So I'm going to just kind of talk to you about this. So what you would have been doing would be, I would have given partner A this card, and partner B would have gotten this card. And so partner A would have talked to partner B and tell them, basically they would try to describe how to draw what they were seeing. Alright, so let's kind of talk about this for a second. Let's talk about, here's my original and here's my image. How did I change here? Alright, so I'm trying to figure out how I went from this image to this image. So study that for a minute. And notice that they kind of flipped, didn't they? Alright? Let's look at this one. So basically I want to know how did I go from this image to this image, and I've got point G here, so I'm using point G. Well, you kind of have to look at this, and it takes a little bit of studying to figure it out on what they did. So maybe if they rotated it, would that work? Maybe. Alright, and then the third one, I want to know how I went from this to this. And notice I have a line here. Alright, what happened here? They just split it. Okay? So, here's what you need to take out of this lesson. And there's a couple of things we're going to write down on the back of our paper. Functions that take a set point as inputs, apply a given rule, and output a new location for an image of the input points. Basically what it's telling me, okay, so if you think about it, when you guys have been introduced to functions, you are introduced to a function machine. In other words, I put a number in, something happens inside, and something comes out. Let's say the rule was add 3. If I put the number in, if I put number 1 in, it adds 3, so I get a 4 when it comes out. If I put the number 2 in, it adds 3, I get the number 5 coming out. So that's what it's telling me here, is that transformations as functions take a set of points, they do something to it, and it gives me a new image. The input points do not move, nor does the plane. You can think about this as a fax. Alright? You all probably don't send fax a whole lot. But when I go and send a fax, if I need to send something to another company, I can go to the copier and I can push in the phone number that I want to send my fax to. I put it on the copier and it scans it. But here's the thing. The person sending the fax keeps the original copy. The original copy doesn't go anywhere. Alright? The machine simply sends an image to another location. So, if you look at this, that's what's happening. Here's my fax. I'm sending an image, but my original stays. Alright? So, a little bit of an analogy there. You must understand that two transformations are the same if they produce the same image. So, let's say that I have f of x. This is a function. Let's say that I have f of x is equal to x squared minus 1. What you need to understand is I've got g of x is equal to x plus 1 times x minus 1. These two functions are the same because they give me the exact same thing. If I were to actually multiply this out, I would end up with x squared minus 1. So because these functions give me the same image or same thing, they are equal. Even though I'm going through different processes, different procedures, they still give me the same value. So they give the same input, both outputs are identical, therefore these two functions are equal. And this applies to geometric functions as well. Alright, so let's look at this. Let's look at our discussion. This is probably some of the most important discussion that we're going to have. The word transformation, explaining how to transform figures without the benefit of a coordinate plane can be difficult without some important vocabulary. So let's review. The word transformation has a specific meaning in geometry. A transformation, f, of the plane is a function that assigns to each point P on a plane a unique point f of P in the plane. Transformations that preserve lengths of segments and measures of angles are called blank. These are called basic rigid motions. Transformations that preserve the length of segments and measures of the angle. In other words, nothing changes. It still has the same shape, still has the same angle, whatever. These are called basic rigid motions. A dilation is an example of a transformation that preserves blank. It preserves the angle measures, but not the length of the segment. Because think about the word dilation. Dilation means to make bigger or smaller. So I'm not preserving, I'm not keeping the same length, but I am keeping the same angle measures. In this lesson, we work only with rigid transformations. We call a figure that is about to undergo a transformation the pre-image, while the figure that has undergone the transformation is called the image. So we have the pre-image, which is what we start with, and then once we do our transformation, we have what we call the image. Alright, so this next page here is going to go through some of these transformations. We have a rotation. Rotation means I simply rotate it. I move it around. Then we have a reflection. When you think about a reflection, think about the mirror. When you look at yourself in the mirror, you are backwards. That's what's happening here. I'm backwards. Then we have what we call a translation. A translation is basically a slide. I'm sliding it. Notice I didn't change the direction that it was facing or anything like that. We can call a rotation a turn. So it's turning here. Alright, a reflection can be a flip. And then our slide, our translation. Okay? So these are the three types of transformations that we're going to be talking about. Using the figures above, identify specific information needed to perform the rigid motion shown. So for a rotation, what do we need to know? Well, for a rotation, we need to know the center of rotation. In other words, there is a point that does not change when I do a rotation. Alright? It could be a point right here. It could be a point up here. But somewhere there is something that I'm rotating around. We also need to know, are we going clockwise or counterclockwise? So we need to know our direction. Alright, and when we say that, we would need to know, are we going to turn clockwise? And that's CW. Or are we going counterclockwise? Alright, and we call that CW. Alright, so for rotations, we need to know where's the center of rotation. We also need to know what direction we're going in. And we need to know the number of degrees rotated. In other words, am I going to rotate 90 degrees? Am I going to rotate 85 degrees? Am I only going to rotate 20 degrees? how much am I going to rotate? In other words, how far am I going to rotate my figure around? Here, you can see it didn't quite do a full 180, because if I did a 180-degree rotation, my R would be standing up on its top. All right? So those are the three things that we need to know for a rotation. All right, let's talk about a reflection. For a reflection, here's what we need to know. We need to know the line of reflection acts as a perpendicular bisector to each segment that joins a given vertex of the pre-image with the respective vertex of the image. So in other words, I need to know, where did I reflect? All right, so looking back up here, I need to know, did I reflect this way? Did I reflect from top to bottom? Did I reflect from left to right? Did I reflect from right to left? Where did I reflect? All right, so where's my line of reflection? All right, so for translation, here's what we need to know. We need to know the point P to be translated. All right. We need to know the length and the degree measure of the angle that the vector makes with the line that passes through P. And we need to know the end point of the vector. Okay? In other words, I need to know where I'm going to start my rotation. I need to know how far or to what degree I need to make my rotation. And I need to know where to stop. Where am I going to stop with this rotation? All right, so these are the things that I need to know. All right, so geometry assumptions. We have now done some work with all three types of rigid motions: rotations, reflections, and translations. At this point, we need to state our assumptions as to the properties of basic rigid motions. Any basic rigid motion preserves lines, rays, and segments. In other words, they don't change. If it's a line to start with, it's going to be a line when it ends. If it's a ray when it starts, it's going to be a ray when it stops. That is, for a basic rigid motion of a plane, The image of a line is a line, the image of a ray is a ray, the image of a segment is a segment. Okay? Any basic rigid motion preserves length of segments and measures of angles. So in other words, the length of my segments and the measures of my angles will not change when I perform a rotation, a reflection, or a translation. Alright? Here you've got some relevant vocabulary. I would suggest you take time to read it. I would suggest you make sure you understand it because you are probably going to be seeing it more. If you have any questions, please email me. Give me a call at school, leave me a message, I'll give you a call back. The best way is to email me. I will get back to you as soon as I can. Guys, if you need help, reach out.